In this video, I want to give us some general rules about graphing our exponentials. So in the last video, we spent some time looking at 2 to the x power. And we saw our nice little exponential growth, just like we see here in this graph, right? And we could even click around on this graph and see, yes, we have our 0.01. We have the point we talked about before. Come on now. It's not going to let me click on it. Well, we have 2, 4. And we have 3, 8, just like we had before. So what would happen if we change this up and we did y is equal to 3 to the x? And before I even do this, you should have an idea in your head about what's going to happen to our graph. And you can see it goes up even steeper. It actually decays slower over here, though. It gets lower faster, and it's steeper in our graph. It still goes through the same point. And that makes sense because remember, that point is when we plug in 0 for x. And 3 to the 0, anything to the 0 is 1. So it doesn't matter which base we choose for our exponential. We could do 4 to the x. As we do this, no matter what, it's always going to go through that same intercept. The only way we're going to change that intercept is by adding something, subtracting something, multiplying by a coefficient. But anything where it's just this basic exponential, this is what we're going to see. Now, what we've been looking at are all examples of exponential growth. And all of these, the base of our exponential function has been larger than 1. In fact, if we try out like y is equal to 1.1 to the x, you can see we are still going through the same spot, but now our growth rate is so slow that we have to zoom way out to even see that curve, that exponential growth. But it's still growing. So the counter example to this, I realize you guys can't see my colors, so I'm going to try to change this window size a little bit so you can see which color goes to which graph. So now you can see the colors in Desmos. The alternative to this, I'm going to go ahead and delete all of these extra graphs, and we'll just go back to our friend 2 to the x that we know so well, is if y is less than 1. So what if y, the base here, not y, but our base was less than 1? Say it was 1/2. So 1/2 to the x power. Now we get what we call exponential decay. Things are cutting in half and in half and in half and in half, and they're going to approach 0. It's actually the opposite of what we were doing in terms of flip in the previous example. So before, whatever we had, we multiplied it by 2 to get to the next value at 4, then multiply by 2 again to get to 8. Here we're dividing by 2, dividing by 2, dividing by 2 as we move forward. So this will be the case anytime we have a y, anytime we have an exponential where our base is something less, so 0.6 for example, less than 1, we're going to see this exponential growth. Not growth, decay. I can't speak right now, but hopefully you've been able to follow along. So bigger than 1, we have growth. Smaller than 1, we have decay. Now, there are certain values that don't make sense at all to have as bases. So there are some rules. We can't use 1 as a base because 1 raised to any power is 1, and it's not an exponential at all. We also can't have negatives as our base because a negative, that doesn't work, right? That actually means that for every even power, it's going to be 1. For every odd power, it's going to be -1, and it's going to bounce back and forth. It doesn't fit a function. You can see Desmos can't even graph that. So now we need to talk about, well, the general equation we see a lot in this class. We see a lot of this. We started with tens, or let's go to the rumor question. We started with 7 people who knew the rumor, and then we went ahead and multiplied this with the 3 every single time, right? So this was 7 original, our initial amount, and then our multiplier of 3 new people knowing every single time what was going on. And you can see how this changes our graph. Not only is it steeper because of the 3 as our base instead of the 2, but it's no longer going through that point that we had before of 0, 1. In fact, you can see here it goes through 0, 7. And that's because this piece will always be 1, and then you'll just multiply by your coefficient. So our starting value is 7, and then it's going to triple every single time. So if we wanted to start somewhere else, say start at, I don't know, 4, and then let's say double every single time. Sorry, I need to be able to type in here. Then you can see now for the blue graph, we are going through 4, and then the next value should be at 8. So 1 comma 8 is our next point. So you can see that doubling happening. So that's how that coefficient impacts our graph, and also how the base impacts our graph, because I think those are two important things to understand and what you were supposed to get out of the last JITT.